Hi everyone. Today we're doing a video on optimizing performance using Unity for an OpenXR project, specifically getting fine-tuning to target an Android build like the Meta Quest 2 or the Oculus Quest 2. So let's talk about how to get started. So the first thing you'll notice here is I have an empty scene in Unity. This empty scene is created using the URP template. So starting with URP is probably the number one choice. It'll give you the best balance of performance out of the box. Let's go into project settings after you have your initial scene created here. One of the first things you're going to do is you're going to click on time here in project settings, and you're going to go to fixed time step. So fixed time step is basically the frame rate at which the physics is calculated within the game. So my value here is already set, but a quick way you can set this is to do 1 divided by 72. So the Oculus or the Meta Quest 2 will run at 72 frames per second by default. So putting this number in there, hitting enter, will get you the right fixed time step. So with that set, let's move over into the quality tab. Your URP build out of the box will have different quality settings. So you'll have probably a low, balanced, and a high. I basically removed the low and the high, just kept the balanced profile. The balanced profile is balanced, so it's a good starting point, and it's a lot easier to troubleshoot performance in your builds when you're not mistakenly targeting a different quality level with, let's say, a editor build versus a build on the actual headset. So try to eliminate this, keep it down to one build. Some of the other settings you can have is texture quality. So you can basically force different resolutions of texture quality. Mine is set to a quarter resolution. This is something that you can adjust and play with. Other things you want to check in here is that one, your skin weights for your skin mesh renders. This is your animation quality and performance setting. So I have this set currently to 1 bone. You can set this to 2 bone. It's probably not a large performance difference, but depends on the quality of the animations that you want to see within the game. So right now mine's set to 1 bone. You could definitely set that higher if you needed to. Moving on to some of the other settings here in the editor. Right now I'm under other settings under player. So for color space, linear or gamma are relatively close in terms of performance. So there's probably not a big difference between them. Right now I'm using OpenGL, so I'm targeting linear color space. Besides the linear color space, the graphics API doesn't have too much of a performance impact. I am using 3.2 here. So we'll walk through some of the other settings here under the player menu. So multi-threaded rendering, static batching. So static batching is something else we'll talk about here on optimizing performance. Compute skinning, graphics job experimental. Texture compression format is ASTC. So you want to just go ahead and set that here in the menu. Lightmapping coding, I have it on normal quality. If I scroll down here, I'm not using Vulkan currently, so I'm not actually checking any of those boxes. You want to make sure that your minimum API level is set to level 23. Your target architecture needs to be targeting ARM64. So ARM64 is the requirement currently for publishing into the Oculus store. All right, now that that covers the project settings, let's go over to our URP settings here. So again, I have my URP balanced. I do have some other ones in here that were left over from the template. We're not actively using them. So for URP balanced, some of the settings in here I don't have enabled. Transparent receiving shadows, native render pass. I don't think this is compatible with OpenGL. There's not many settings in here you actually have to modify. I am using the decal renderer feature. So right now I just have a couple of settings on there because I am using the URP decal projector. As far as rendering something like depth priming mode, I currently have that disabled. Going into URP itself, so you'll see it has a reference back to that file that we were just looking at. let's expand the quality settings. So I do have, well, let's talk about the rendering first. So I am using depth textures in my shaders. So I am enabling depth texture. Opaque textures I am not using, so that is disabled. And I do not have terrain holes enabled. For quality, I'm not using post-processing effects, so HDR is disabled here. For MSAA, I am using 2x, 2x and 4x. There's not a big performance difference, so you can kind of tune and experiment with these based on your game. Render scale, so we'll talk about this a little bit more, and you can kind of dynamically set this if you need to. Right now, mine's set to 1, which is the default setting. Upscaling filter, this is just automatic. Lighting. So lighting will have its own dedicated section here, but right now I'm using per pixel lighting, which basically is fairly expensive, and I am actually using shadows. I have changed my shadow resolution to 512. Generally, shadows are discouraged in VR games because of performance reasons, and if you look at a lot of big VR titles, especially ones that are on something like the Meta or Oculus Quest 2, you'll see that they actually turn off shadows on quite a few things. So they're using baked shadows, but not real-time shadows. For me, I'm actually able to get real-time shadows. So I'm just changing the resolution on those for performance reasons. Additional lights. So this wasn't really changed. Right now, it's just set to 2, which was the default. I don't have cast shadows on. And I'm not using reflection probes. So these are just unchecked here. For shadows, I came in here and I basically set a distance. So right now this is set at 150. You could definitely lower this. It will affect general shadows, even baked shadows. So depending on your view distance inside of a scene, could give you some different effects. So just be aware of that. Working units. Right now it's percentage based, and I'm not using cascade shadows. So I'm effectively keeping the same shadow at a consistent quality level over my draw distance. So you can experiment with this a little bit. It really depends on what's going on in your scene in terms of how many dynamic shadows you have, which is probably where you'll see some of this performance benefit. And you can essentially just change the cascade count, and you can have different shadows at different distance benchmarks. So this will give you the ability to vary the resolution. This can be helpful, but again, it does require some processing power. So, that it has to compute that distance, compute the quality of shadow, and switch between them and maintain that. So right now, I have them disabled. It seems to work for me and gives me consistent results. For post-processing, I do have it set on low dynamic range with fast sRGB conversion. Going over to our scene setup here. Right now, I have just a simple camera as it comes created with the scene, no special settings, a directional light, and a quad that's just serving as the ground in the scene. So clicking on the camera, this is set up basically, as I said, out of the box. The clipping planes have not been adjusted. Render shadows. There's really nothing here that's overridden from the default camera, and it is referencing the render pipeline asset for things like shadows and HDR. Now, with this camera, the main light source in the scene here is this directional light. So lighting is our first topic. So in order to get the best performance out of your game, one of the things you'll probably realize very quickly is that you'll be GPU bound on the Meta Quest 2 or the Oculus Quest 2. So one of the big topics here is lighting, because lighting is obviously very important into a game to create atmosphere, create certain effects. So things like real-time shadows or baked lighting are definitely core to getting the most performance out of your game. So in my scene here, I have this directional light. Right now, it is set to real-time. There's real-time mixed and baked. Mixed will give you baked lighting with real-time shadows on dynamic objects. This is what I use on pretty much all of my scenes, so you can just switch this to mixed mode. Other settings in here, such as intensity, light color, you could change that based on your scene, your skybox, whatever the particular atmosphere you're going for. Other than that, You don't have to change much inside of the directional light. So I'll switch over to the lighting tab here. You can get there from window, and then you can go to rendering and lighting. So the lighting tab here is currently disabled. Let me grab a, okay, so I have my default light settings. We're not using real-time global illumination. It's a lot for the headset, so we're going to focus on baked lighting. So if I come in here and I click baked global illumination, that will enable all the different light mapper settings. I have mine just saved under a particular setting file. You can do the same with yours. These particular settings in here are basically the quality of the light map. It won't have a direct impact on performance. It will more or less be kind of quality settings. So one of the big things in here that you'll probably want to change right off the bat is the light map size. 2048 is usually where I've stuck at in my particular game. I do have ambient occlusion on too, so I'll just make these two changes. Other than that, there's not many settings in here that have to change. If you're looking for better, higher quality light maps, you can change the light map compression. You can up the resolution. Sometimes you also have to change the light map resolution here in the light map padding. The padding can sometimes create seams with the models, and depending on how their UVs are laid out. So now at this point, we basically have a scene with a camera, directional light that's set up for baked light mapping. There are no light maps currently. And we have a quad. So if I go in and I play this game at the moment, when we switch over to the game scene here, we'll notice that the game scene will have this statistics window. So you can click stats here to show this particular scene. But what's very interesting here is you'll notice a couple of key benchmarks. You'll notice that your time spent on the CPU, basically rendering, your batches, how many draw calls you have, triangles, vertices, and saved by batching. So we'll discuss these a little bit in detail later. So now that the scene works, I'm going to go ahead and just add a simple 3D object, just this cube here. You'll see the shadows aren't great in the scene right now, and these are just, again, settings. So now that I have a simple object in my scene, when we click on back to the inspector view, we'll make sure this item is highlighted, and we'll talk about the mesh renderer. So the mesh renderer is any 3D object that's being rendered onto your scene. And there's a couple of really important settings in here, and we'll go over changing them, what effects they have. One of them is material. So we'll skip over this for right now because it is using just a generic out-of-the-box material that comes on this 3D cube. Cast shadows and contribute global illumination. So when I go into my game and I have this 3D cube now, when I run this particular scene, I'll be able to see the draw count should increase. So I should see my batches have went up, and I have 2 shadow casters. So this is actually pretty important here, the shadow casters. This means that I have some type of dynamic shadow casting object in my scene. One of the things you want to do to really kind of drill into how my scene is configured, that I possibly miss some items that are contributing shadows and really kind of eating into my performance budget. One of the things you want to do is go into analysis and click on frame debugger. So frame debugger is right down here. I'm going to click enable. So when I enable it, it'll show me basically all of the details that are being rendered into the scene and different render passes. So I'll just collapse these real quick. When I click on main light shadow, I can instantly see that there are 2 different objects in my scene casting shadows. So if I click over to game view, it'll actually show me what the rendering looks like when this is complete, this phase is complete. So when I click on this, you'll see, try to scroll in, this cube here that's being drawn, and then the quad right after it. So these 2 objects are casting real-time shadows, even though I'm configured for using baked lights. And this might make sense because we haven't baked the lights yet, but let's just experiment with something real quick. So if I turn off cast shadows, you'll see it updated right away within the render. Now, If I come in here, I'll turn cast shadows back on and I'll say this is contributing global illumination. Now I can choose how does it receive the lighting from the scene. So without this, it's a dynamic object. With this, it is now a baked object. Now, when I click into the options for receive, there's light maps and light probes. Generally here, and Unity has great videos and documentation on this, light maps is something that large objects in your scenes, focal points that need really precise, well-defined lights and shadows, light probes, are generally for smaller details that can receive lighting from light probes without that fine detail in it. So if I just leave this light maps and I hit play, one of the things we'll notice is that it'll still say 2 shadow casters. So right now I have an object here and the editor says it's static, but it still says 2 shadow casters. And that's because we just haven't baked the lights in our scene yet. So anytime you're in a scene and you're making changes, even if you check the global illumination box, unless you go through and you actually bake the light maps, so I just went ahead and baked the light maps, you won't actually see the shadow caster count reflected within Unity. So you'll see that it's just at a 1 now. And the main reason for that is because we haven't set the quad or the floor to have any kind of static flags. So for light maps, generally, you're tuning it for your scene in terms of the ambience. Frame debugger here is great for finding out what objects are being rendered onto the scene. So you can see things like transparent objects and some of the batching within Unity all comes from the frame debugger. The game view and the statistics of the game view as far as batches and the amount of shadow casters, definitely important. And making sure after you apply updates, you're going back and you're baking your light maps, because without rebaking it, you won't see that number change. So you need to make sure you rebake. Now, the second part of this video is going to be talking about the render passes and the expense generated rendering an object. So in our example here, we have this cube, which has this lit material. Now, this lit material is really just a simple material here that's created that has a color applied to it. So if I went into this material here, this is one that comes with URP, but we can quickly kind of generate our own here. So let's go into Unity somewhere, and we will put a simple material in here. We'll just call it new material for now. And we'll go ahead and just pick some color. One of the things that's very important in terms of rendering performance is the shaders that are applied to your materials. So transparent shaders are very expensive. Alpha blended a little less expensive, and some of the mobile shaders are really good if you need to do some kind of transparency, let's say on particles or glass, or something like that. So in this particular case, simple lit does have some drawbacks. There's good documentation on it on Unity, but essentially it does kind of light approximations where Unity is spending less time spending shadows and drawing all the different light features on that particular object. So making sure that you're using inexpensive shaders is very important. Simple lit and some of the mobile shaders for particles are kind of my go-to. So that's generally the topic on expense for rendering. Now, when you want to render multiple objects, so as an example here, I will take this cube, and the cube here is just a normal 3D cube. I'll duplicate it, move it to the side for now, and what I'll do is I'll make these both not static. I will clear our light map data. So now they are both dynamic shadow casters. And basically when URP draws this, so when we go ahead and launch the game here, we'll notice that it spends a draw call on both cubes. So if we go into our frame debugger here, so when I click into our frame debugger, you'll see that we have two cubes that are shadows. And we will see that also under draw opaque objects. We'll see those as well. So if we come into these cubes, and we'll just click the static box for now. As you know, there's a bunch of different static flags. So we'll talk about static batching, dynamic batching, GPU instancing. So when we play the scene, all we've done is basically check the box telling Unity that this is static. So one of those options are static batching. Now, when we go into Unity, we'll notice that the batches call, instead of saying 8, we'll say 7, and it'll say it's saved 2 batches. Now, if I click the frame debugger, when we look at shadows here, you'll notice that static batch shows up instead of draw cube. And you'll also see static batch down here show up because it is now batching these two cubes together. Now, static batching, or the SRP batcher in Unity, does have some limitations. So it's important to understand when I might use static batching and when I might use something like GPU instancing or mesh instancing on a material. So right now, with these two cubes marked as static, I'm going to uncheck them. I'm going to go and drag my custom material on these, and it applied to both. And I'll rerun the scene again just to show kind of a baseline here. So really all I did was switch out which shader. It doesn't have any effect on this particular scene. And you'll see that we're back up to 9 batches with 0 batches saved. So if I go into the new material and I'll click GPU instancing, and I will relaunch the scene. So GPU instancing is applied at the material level, where the SRP batcher is applied at the object level. So you'll notice here we get the same output. We'll have 7 batches, 2 saved by batching. And when we go into the frame debugger, you'll see draw mesh instance and draw mesh instance, so under shadows and opaque objects. Now the key understanding here, well, there's a couple. One key understanding is that the GPU instancing that happens on a material is actually only applying if it's the exact same mesh. So if I come in here and I create a cylinder, and I'll just remove my cube out for now. So with my cylinder here, even if I apply that same exact material that's using the GPU instancing, so the mesh instancing, because they're different meshes, even though they save the same material, you'll notice that the draw count here will be 9 and nothing is saved by batching. And essentially that's because they're different meshes. Now, if I come into here and I mark these both as static, you'll notice it'll give me a warning saying that the material has instancing turned on, but you're marking it as static. I'm just going to go ahead and try to statically batch them instead of using mesh instancing. So when I load Unity, you'll see we're back here at 7 batches with 2 saved by batches. So hopefully you can kind of get an idea of the different use cases of these. So if you had, let's say, rocks in your scene, or maybe a fence, something that was very repetitive, maybe there's a lot of them, you might save more performance by mesh instancing them versus static batching. So it's really important to try both if you're running into performance issues to see which one gives you the most benefit. Now, one of the other things to note here is that when I hit play, it also depends where my camera is at in the scene. So if my camera is not visible, or sorry, if these objects are not visible within my camera. So if I took my main camera here and I just dragged it way over here, you'll see that I won't see any of this information at all. And that's because my camera is not rendering it. So another important bit here is to say, when you are experiencing a performance issue in your scene, it could be localized to a particular area of the scene, meaning that you want to probably move your camera to that exact position, maybe rotate it a little bit, try to understand exactly what's in view of the camera and what's actively being rendered. This kind of brings us into our next topic here, which is the frustum and occlusion culling. So by default, Unity has this frustum culling, which is, essentially these white lines here on the camera. The camera has a field of view. It's a defined kind of box that it's able to render within. And then you have the clipping planes, right? A near and a far, and that's the distance of the drawing. Now, what's really interesting about the performance optimizations that Unity gives you out of the box is when you go into something like a mesh renderer, you'll see dynamic occlusion is turned on. So this setting you could pretty much leave on, and it is on by default. Now, occlusion culling specifically. So if you go into Window and you go into Rendering, you can click on Occlusion Culling, which will bring you to this occlusion menu here. Basically, what you want to change is the smallest occluder and smallest hole. So it depends on your scene. The ones that have worked great for me and my assets and the scale that I'm working at has been 2 and 0.2. Now, when I go into visualization here, it'll kind of show me what is being occluded. So now, right now, you'll see there's really nothing going on. So I'll go into Bake. I'll click Bake here just on the bottom right. And you'll see Unity will go and create these cubes for me. And essentially, if I go into the camera here and I move it around, you'll see that Unity will highlight and show me the different occlusion volumes or kind of bounding boxes that are within the setup. So you'll see that when it goes out of view, this cube right here disappears. And this is basically occlusion culling. Now, one of the things you can do is we'll just create an empty object here. And we will go into occlusion area. So occlusion areas are basically a way to fine-tune occlusion culling past the settings in the occlusion window. So an example of this would be maybe there's a particular place where the player is at, and you have the camera, and we want to create a special volume where we have very high fidelity occlusion data, and that's what this is. So you can essentially just put this in your scene. If your scene's small enough, you might be able to just wrap your whole scene in it. But the idea is that you can put this around and then go in and you can bake again, and Unity will generate higher resolution. Now, for occlusion culling, the really interesting part is it doesn't solve all of your problems. It solves a lot of problems with very small objects, and especially in interiors where the camera's in these tight corridors and you're kind of restricted on your surroundings, right? So maybe you're in a hallway or you're in between buildings in an alley, and maybe those buildings are populated with lots of detail, right? So occlusion culling is definitely a big compute saver there. You're not rendering those details behind an occluder. So with these terms, occluder, occluding. So if I click on this cube here and I go back to static, there's occluder and occludee. So occluder means that it's a big enough object that it could potentially block an object. So if I went ahead and I increased, let's say, the scale of my cube here, and I wanted to essentially, right now it's set as an occluder, and I have this cylinder behind it, and it's checked too. So it is an occluder itself, but it's also an occludee. So if I go in, and because my scene has changed, I want to just bake again. Actually, don't need to run the scene. I could just use the visualization tab. But as an example, when we run the scene, so you'll see that this particular cylinder is not actually rendered, right? Because it is behind this occluder. So even though the camera is looking that direction, it technically can't see it, so Unity will not render it. So this is a good generalized way to see, what am I actually rendering? What is occlusion culling saving me by using visualization? So this basically covers occlusion culling. So the key takeaway here is that you want to actually have your items marked static if you can, occluder or occludee. You're going to play with the particular settings to see what gives you the best benefit. And again, it depends on where your camera is. So it's important to move your camera around different parts of the scene and really see how well it's working. And the easiest way to do that is with the visualization option. So at this point, we should start seeing some pretty big performance benefits in our game. So with things using like simple lit, baked lighting, some of the lighting features, static batching, mesh instancing, occlusion culling, a lot of these features should get us to a pretty stable frame rate. Now, what happens if you're still kind of running into different bottlenecks within your game, and it's very hard to tell exactly what's causing the issue? So one of the things you can do is go into the profiler, and then you can actually profile the different pieces that make up the render loop, right? So you can look at CPU usage, you can look at rendering and physics and animation, garbage collection. You can look at the rendering stats here. I do like the game stats; they're a little bit easier to consume. It's similar data here. Memory, physics, audio, UI, global illumination, etc. So the profiler is great, and if you're profiling code, there's a couple of things to look for. One of the things to look for is garbage collection. So inside of your project settings, there should be a setting to enable. I believe it's under player here. There should be an incremental garbage collection setting. Use incremental garbage collection here. So you want to make sure that this is enabled. So this allows Unity to spread the garbage collection out over multiple frames. Ideally, inside of your game, you don't want to have any garbage collection if you can. And we could talk about some ways to eliminate that. So as an example, I'm going to go onto my cube object here, and I'm just going to create a new script, and I'm going to call it my GC test script. Now, this is an example of some things that could cause a lot of different garbage collection within your game. Some of the common pitfalls that you're going to run into with interacting with like physics or ray casting, or just different functionality within your game. So what I'm going to do is open up this GC test script that I just created inside of Visual Studio. And we're just going to run some pretty simple tests. So one of the things we're going to do is we're going to do a physics raycast, and we're going to do it basically from the perspective of our, in this case, it's the cube. So we're going to raycast out, and we're going to raycast 5 units in our forward direction. So in my GC test script here, we have our raycaster, and what we are going to do is basically output the raycast hit information. And essentially, what we're going to do is we're going to look at the results to see exactly what the raycast hit. And we are going to say on the game object itself, we are going to try to resolve our GC test object and just say, test object. And basically, this raycast is going to be running an update. It's going to be raycasting in the forward direction, and it's going to be checking for a component on whatever this particular object hits. So just to make this a little easier, I'm going to go ahead and scale this cube back down. And we're going to take this cylinder here, and we're going to just scale this cylinder up. And this cube should be right in front of it. Now, at this point, the cube should be raycasting out, and it should be hitting an object. And this is happening in the update loops. It's going to be happening very quickly. We're going to go ahead and go to our profiler tab here. So as soon as you click the tab, it'll become active. Right now, I just have scripts and garbage collection enabled. And we're going to watch the chart here. And one of the things we'll see, let's see if we can catch it here too, is the player loop. So the player loop is actually what we're interested in. We want to see exactly what kind of code is running within our custom code. So I'm going to go to player loop here, and I will see this garbage collection allocation. I'll see it on the update, so it's happening on some update. And I'll expand it, and it'll say GC test and physics raycast. Now the raycast doesn't actually create the garbage. What I'm going to do is I'm going to click on deep profile. So deep profiling is sometimes important to see exactly what's causing the garbage collection. At this point, deep profiling is on. We'll just rerun the game. The profiler will start back up. And once it starts running here, it takes a second. We'll see these little spikes. We'll click on, again, one of these spikes here. And we'll see that in our script, the actual culprit of the garbage collection is this component get component. Now, you'll notice that it calls this get component fast path. So to me, the usage of get component is actually really important for situations that you know you have the actual component available. So if you didn't, let's say you needed the same code and you needed to get the component off of this object you're interacting with. But one of the things you can do is you can use try get component, and you can actually say try get component, and this returns a boolean, so you can check to see that it was successful, and then if it was, you can do log test object. In this particular case, it won't be because the script's only attached to one object. But with try get component, it's actually a lot cleaner in terms of the garbage collection. So if you had a lot of testing for different types of components that are available, one of the things you want to do is stick with try get component. So we have try get component currently in place. Let's go ahead and rerun it. And we should see this start up. And we will click, and we will see that even with these spikes here, the garbage collection is not actually happening anymore. So the garbage collection is fixed with just switching over to try get component. One of the other things that is pretty common in terms of garbage collection is using different types of collections in .NET. So as an example, using a list or an array. Arrays are technically a little faster. They don't have the same type of overhead when you're iterating through them. The arrays are just much higher performance. And to give an example, if I create an array of our GC test script here, one of the things I have to do is size my array, right? It's a fixed size construct, right? I have to say that my particular array here is a size of 32. I can put 32 objects, that's it. Now, when I use a different, like a generic collection, such as a list, for GC test, and I say, this other test, I can new it up without providing this size. Now, the list and generic collections will resize based on the capacity of them. Out of the box, so let's look at one of the constructor arguments of list. You'll see that capacity is here as a parameter for this constructor. We can pass in the default list size, I believe, is 100. So with 100, as you start getting near that limit that's within the list will actually keep resizing. It'll keep allocating memory. So as you're using a list and you're changing the bounds of that list, internally, .NET's resizing. It's allocating memory. It's allocating memory. And one of the most important things to do is if you define a list, try to treat it like an array, give it a capacity, understand what your capacities are. Don't just put some, obscenely large number in here. Try to be realistic with it, just like if you were using an array, or stick with arrays. And then equally with a list, one of the important things is iterating over the list. So the whole enumerator portion of the generic collection is definitely performance intensive. It's not something that's going to matter if it's here or there in your code, but if you had enough of them, it could add up to a little bit of your performance buffer. So lists are kind of my go-to just in general. So outside of this, these are pretty common ones. And again, in physics here, there are some non-allocating versions of the raycasters. I would strongly recommend sticking with these if you have some need to query lots of objects within your scene. Another thing to note with these as well is that when you switch to the non-allocating ones, you lose the ability to process sequentially. So if you use the raycast non-allocating, the results that come back within the results array are not sorted by distance, which is kind of a big deal. So in some cases you can, in some cases you can't actually use this feature. Outside of that, for performance tips, that mainly covers all of the topics that I wanted to. There are other tips and tricks here that you can do to get performance benefits out of your game, but this covers the majority of the high level ones. Fine tuning your game is probably going to end up coming down to draw calls, the number of vertices, the number of triangles or polygons within your scene. The draw count and the game statistics here are really key. I've found that on average on my game, right around 120 draw calls, I started getting performance dips. So it's important, and you'll kind of learn the characteristics of your game based on your assets and your scene complexities. So one other quick performance tip that I want to share here is right now in our scene, we have basically two 3D objects. If we go into this cube here and the cylinder here, we'll reset the scale on the cylinder, and we'll look at our layers that are attached to these. So let's say we had a number of fine details that were in a scene, let's say like a grass or bushes, something that were small enough that we could kind of vary the draw distance, but we couldn't really solve the problem with the camera's far clipping plane. So we can't reduce the view distance too much because there's enough environment details in the skybox, and it would just cause some ugly artifacts. Well, one of the things we can do is change the draw distance for a particular layer. So in my cylinder here, in my game, I already have one called detail, but I'm just using a simple layer, assigning it to the cylinder here. And right now, the cube is on default. Everything's on default. And we've got the camera here. Now, with this particular setup, we need to tell the camera, well, we're going to just reuse this GC test script here. We need to tell the camera we have a particular layer, and this particular layer needs to have a different draw distance. So what we're going to say is we're going to come up with a new float of 32. It's an array. The 32 here is the number of layers within Unity. And we're just we'll grab a reference to the camera object real quick. And we will say camera layer call distances equal distances here. And the array in this index is essentially your, the index in this array is essentially the index of your layer within Unity. So if I just go back to Unity real quick and I click on the cylinder, this one is 20. So that, that would be our particular index here. So, oops, if I come in and I say 19, well, actually, no, I believe 0 is already that. So I will set this to a small number like 5. And then at this point, I have to add this script, somewhere on the scene. It's already grabbing a reference to the camera, so the script doesn't have to be directly on the camera. But when I go in and I play the scene, the script should still be attached to my cube. We should expect to see this particular layer not drawn, or not being drawn. So the idea here is that the cylinder exists, but the camera is beyond the particular view distance for this cylinder. So you'll see that the cylinder pops in as I move the camera within the distance. Now, this, obviously needs to be, kind of controlled with, some other technique. So you might see one like, maybe fog, um, where, you have some kind of fog in your level, and, the fog is kind of, drawing over, the distance and kind of occluding that particular set of objects so the player doesn't notice the pop in. All right. Thanks. That about covers all the topics on performance here in Unity. Again, this was basically targeting a low-end Android device, the Oculus or MetaQuest 2. And in terms of VR, this will probably get you most of the way there. If you have any other suggestions or something that's maybe helped your game out, please leave it in the comments below. Thanks for watching.